Carried. Okay, so yesterday, when you were messing around with your calculator, anytime we had a cosine versus a sine in our equation, something happened. Every time, no matter if it was a circle, one of those flower things, one of those lily pads, if there was a cosine, what was special about the graph? If there was a cosine, if it was a circle, a rose curve, or a limacon, if there was a cosine, there was some sort of symmetry. Okay. No matter what kind of equation we're working with, if there's a cosine, there's going to be horizontal symmetry. We could fold it in half over the horizontal axis. I can't really call it the x-axis because we're in polar form, okay? The horizontal axis, and it's the same top and bottom, okay? If there's a sine of theta in our equation, then we would have vertical symmetry. Now, I feel like this makes sense because if we think about cosine is always associated with x in everything that we've done. And sine has always been associated with y. Unit circle, vectors, polar coordinates, okay? So I feel like that makes sense, all right? Now, we're gonna talk about what you did in that section 1. We're gonna talk about circles. There are two ways to graph a circle. The first one is if we have r equals a number. And we talked about this one way back on Tuesday. Yes, the pole is the origin. I did, and it's okay. The pole is the origin. That's why we call them polar coordinates. Okay, so if we have r equals a number, we have a circle with radius, that number, centered at the pole, aka the origin. Okay, and this is, you converted ones like this a few different times on Tuesday. R equals 5, that means x squared plus y squared equals 25. Okay. What we really care about, though, what you graphed in your calculators yesterday were circles that were tangent to the pole. Okay. So remember, I kind of asked you about the one from our warm-up. R equals 4 cosine theta. Okay. And you told me if there was a cosine, it was going to be to the right or the left of the pole, right? So what you wrote down first was f of cosine theta, like a function of cosine. Okay. So right now I drew this to the right. Okay. What would my equation need to have in order for this circle to be to the left of the pole? A negative. If we have a negative a, it flips to the left. Okay. And then if we have a sine theta, where does our circle go? Up, you said? Okay. How do I get it below the pole? A is negative. Okay. A is representing the blank of the circle. I disagree strongly. Okay, so look at the circle. From the origin to A, what do we call that in a circle? Say it louder. Okay, and said diameter. Okay. In this case, when we are tangent to the pole, so A cosine theta or A sine theta, we have a circle with a diameter of A. Okay. We're gonna graph. We're gonna graph R equals -5 sine theta. Okay. Take 10 seconds and decide where and how big this circle is. Ready, set, go. You don't understand what? Yeah, that's a polar. Yeah. Okay. All right, Isaac, where is our circle? Right, left, up, or down from the pole? Down. Nate, the 5 tells us what? Okay, so we have a circle. Whew, that looks pretty good. Okay, so we have a circle whose max R value is 5, aka the diameter. Okay, now when we talk about, so every time you graph a polar graph, I'm going to ask you how many zeros there are and what the zeros are. Let's think of a rectangular graph. When I ask you for zeros, what am I asking you for? Okay, the x-intercept, which means y equals 0, right? When we talk about zeros in a polar equation, we're talking about where r equals 0, which means we're intersecting the pole. If r is 0, we're at the pole. Okay. Okay. So, first of all, when we draw this circle, okay, when we draw any graph, like when you put your graph into your calculator yesterday, you know how it kind of like would draw, like you could kind of see it go. All right. It's always going to start with theta equals 0. Okay. If I plug theta equals 0 into our equation, what is our R value? 0. Okay. So what's happening in this equation is we are starting at the pole, drawing our circle, and ending at the pole. So how many times did we hit the pole? Twice, because we started there and ended there. Okay. And if being at the pole means R equals 0, then we are going to solve for our zeros by setting R equal to 0. Okay, so what does this mean? 0 equals the sine of theta. All right, where is sine equal to 0? 0, but we started at the pole and ended at the pole, so where's the next time that sine is 0? Up high. That's a really good polar graph. Yeah. Did you like copy paste that so you can use it again?
Yeah.
Okay, good. For the significant points today, we're going to get started and then we're going to use our knowledge of the graph. So you're going to have like 1, maybe 2 things written down for significant points, and that's fine. Okay. All right, how about this graph right here? Write it down. R equals 2 cosine theta. And how about you just draw the graph? Just draw it. Where is the circle? How big it is? Draw it. And it's totally fine if on your paper you just have a horizontal and vertical axis. Okay, that's okay. Joby, where is this circle? Left, right, up, or down? It's to the right. And Richa, how big is the circle? Okay. Oh, that's a cute little circle here, huh? So we have circle with diameter 2. Okay. Now, when I plug in 0 for theta, what is 2 cosine of 0? The cosine of 0 is 1. So 2 cosine of 0 would be what? Okay, so we're starting right here at 2, 0, and then we draw our circle. How many times do we go through the pole? Once. So we have 1, 0. When is the one time that 2 cosine theta is equal to 0? Say a letter, Hank. 5 or 2. Yep. So when I plug in 0, the R value is 2. So we're starting at 0, 2. So if this is where we begin and we draw our circle, we are only going through the pole once to get that circle drawn. Are you with me? Yes. Okay. Because if I put 0 in for R and I solve for cosine, the cosine of theta equals 0 at pi over 2.
There's that pi over the circle on the drawing. Because of it's 2 pi, right? And it's at the other side.
So here's the deal. With circles like this, it's only going to take from 0 to pi to get it drawn. So like if I plug in pi, we would get R equals -2. So here is pi, here's -2. It only takes from 0 to pi to get it drawn. So this is at pi over 2, our R is 0. Does that make sense?
Yeah.
You're going to buy it?
Yeah.
Okay. Honestly, circles are probably the least of our worries today. Okay. Circles are a special version of our rose curves. Why they call them rose curves, I don't know, because they look like daisies and it's always bothered me. But rose curves are very symmetrical and they're beautiful. Okay, so let's talk about those. And you have some notes on your buff sheet that we're going to talk about. So first of all, let's talk about the difference between a rose curve and a circle. Okay. When we have a circle, this n value is 1. We just have theta inside. But when we have a rose, we have a coefficient in front of theta, and we're going to call it n. Okay, so for the sake of consistency, we're going to call those loops like petals. Okay, they're like the petals of our flower. Okay, so we're going to talk about what A and N help us determine. All right. Mallory, what does A determine for our roses? Okay. So since we're talking about rose curves instead of diameter, we're going to say that it describes the length of our petals. Okay, since we have petals that we're dealing with instead of a circle. Okay. How long are our petals? So when I ask you for the max R value, this is what I'm asking you for. Okay. Claire, what does N determine? the number of petals. But unfortunately, it is not as simple as we have n petals. Nick, when do we have n petals? Okay, if n is odd, then we have n petals. But if n is even, Eric, how many petals do we have? Okay. Don't you find that to be weird? I think it's weird. This is why it's happening. Whether you remember this or not, it's not a big deal, but this is why it's happening. When we have an even number of petals, it's taking us from 0 to 2 pi to get all of our petals drawn. Okay. Now, when we have an odd number of petals, it's actually taking us from 0 to pi to draw all of our petals, because from pi to 2 pi, they draw petals that just overlap. They're the same place. So to get our unique number of petals, it is only taking us from 0 to pi when we have odd petals, but 0 to 2 pi when we have even petals. You really don't have to remember that, but I need you to be aware that when you're finding these zeros, so where we hit the pole, you're going to notice that your range of zeros is going to be different when you have odd versus even petals. Okay, and we'll kind of talk about that. Okay. All right, so the big thing today is we need to be able to draw these rose curves, and there's a lot of symmetry involved. Did you notice symmetry in your petals yesterday? Okay, so if we have 4 petals, they're all evenly spaced apart. If we have 10 petals, they're all evenly spaced apart. We're going to use that to help us. Okay. As long as we can figure out where the first petal goes, we know where the rest are without having to do a whole lot of math. Okay. So the biggest part of getting these graphed, we're going to use symmetry to do it. Most of our work will come from finding our zeros. So we're going to do 3 examples in the next 20 minutes. And we'll go slow and we'll ask questions. And you'll have a worksheet for homework with, I think, I'm not even going to remember, 6 or 8 questions, I think. Not a lot. R equals 5 cosine of 3 theta. What I want you to do before we talk about it as a group, talk about how many petals and how long the petals are and what kind of symmetry we have. How many petals? How long are the petals? What kind of symmetry do we have? Ready, set, go. Okay. So we have a rose curve. Bella, how many petals do we have? We have 3 petals. Nicolette, how do we know it's 3 petals? And it's 3. It's an odd number, so we have exactly 3. Okay. Luke, how long are our petals? They are 5 in length. So we're gonna have nice long petals here. Okay. And the symmetry that we're working with is what kind, John? What kind of symmetry do we have? Vertical or horizontal? Would it be? Okay, are we dealing with sine or cosine? Cosine. And cosine we associate with which variable? X. And X, is that the horizontal or the vertical variable? Okay, so what kind of symmetry do we have? Very nice. We have horizontal symmetry. Okay. This is what we're going to do. We are going to worry about finding zeros very last. Okay. we need to figure out where this curve begins. So no matter what you're dealing with, you need to plug 0 in for theta. What's the cosine of 0? 1. 5 times 1. Whoa, I think it's 5. Okay. So 5, 0 is our first coordinate. Oh, that's so nice. We know where a petal is, don't we? Okay. We have 3 petals, and you told me they're going to all be spaced evenly apart. How do I figure out how far apart they're going to be? How many radians go around? We have 2 pi radians that we need to divide up into 3 petals. So 2 pi over 3, 2 pi over 3. There are our 3 petals. Let's talk about how I did that one more time. I know where my first petal is. I have 2 pi radians that we're going to divide by 3 petals. So they're 2 pi over 3 apart. If you don't love radians and you want to think about 360 degrees divided by 3, and you count the 120 degrees, I don't care. We just got to figure out how far apart they are. Okay. Now I'm going to draw this like your calculator would draw this, but I want you to watch me draw it because we need to count how many times we go through the pole. Okay. So this is where I start. Are you ready? You're going to count out loud. Every time I hit the pole, you're going to count. Ready?
1, 2, 3.
How many zeros do we have?
3.
Cool. Well, that's how the graphing calculator is going to draw it.
So we just gotta know.
You don't have to know. Am I going to know that you draw it like that? Or if you go, I'm not going to know. But you have to start at the starting point so you know how many times you go through the pole. But if you make this half and then you make this whole petal and then you make this petal and then you come back, I'm not going to know that. Okay. All right. So now we get to find our zeros. Okay. We know there's 3 of them. And we know that to be a 0, that means R equals 0. And if 0 equals 5 cosine theta, then I can divide by 5, and really 0 equals cosine of 3 theta. It's like we've done something like this before. Way back in chapter 5, right? We solved equations. Okay, now my angle is 3 theta. So 3 theta equals, when is the cosine equal to 0? At pi over 2. So my angle of 3 theta equals pi over 2. And cosine is 0 at 3 pi over 2. But how many zeros did we say this is going to have? So we better have 3 numbers here. We're going to have to keep rotating. When is the next time cosine is 0? So we have pi over 2. We have 3 pi over 2. If we rotate again, we would have 5 pi over 2. I now have 3 angles because we need 3 zeros. But I'm going for what theta is. So what do we need to do to both sides? Okay. So we have pi over 2 divided by 3. 3 pi over 2 divided by 3. and 5 pi over 2 divided by 3. So that turns into pi over 6, pi over 2, and 5 pi over 6. Ask me a question. Good. You want to start at 0 and work your way around until you get the number of angles that you need. So if there are 5 zeros, you want to go until you have 5 angles. If there are 10 zeros, you want to go until you have 10 numbers. Okay, start at 0. Yes. Yes. Okay, because we're talking about just like if you set your calculator to graph from like 0 to 100 pi, it's just going to keep tracing the same over and over and over and over and over again. Like it's not going to be a new shape. Okay, so yes, technically, you know, you could write 17 pi over 2 divided 17 pi over 6 is a 0, but not in that first rotation. Okay, so let's just review what we did. We knew there were 3 petals. We plugged 0 in for theta. Luckily, that told us where we started with the petal. We knew that we needed 2 pi over 3 apart for our petals. When we drew it, we knew that we hit the pole 3 times. So we set R equal to 0 and we solved for 3 numbers. Okay. So now we're going to do one. It's going to be a little different. Good morning. Thank you. Write it down and talk with your pod. How many petals? How big are the petals? What's the symmetry? Okay. Katie, how many petals do we have? Okay. Rachel, why is it 4 petals? Okay, and this 2, which is even, so we double it for our number of petals. Okay. Jalen, how long are our petals? 3. Good. And then Bella, what's our symmetry? Vertical or horizontal? Vertical. Good. Okay, so we will always begin by plugging 0 in for theta. And when we plug 0 in for theta, 2 times 0, 0. What's the sign 0? Ooh, it's 0, isn't it? Here's where we start our curve. That's not great, is it? How do we know where to put our petals? We don't know right now. We know how far apart they need to be. We know how many there are, but we don't know where that first petal is, okay? This is going to happen every time you have a sine graph. Since the sine of 0 is 0, and let me back up, a sine rose petal graph. Since the sine of 0 is 0, then our rose petal is going to start at the pole. So we need to figure out where that first petal needs to go. Now we do know how long our petals are. How long are our petals? We said 3, right? Okay, that's our max R value. So we know R is 3 at the longest part of our petal. So what we can do is we can plug 3 in for R and solve for what that theta is when R is 3. So we know where to put it. So I'm going to divide over that 3. And we just need 1. Okay. Brock, where is the sign equal to 1? Pi over 2. So 2 theta is going to be pi over 2, which means theta is pi over 4. So when theta is pi over 4, our R value is 3. Are we okay with that math? What do we do with it? We're going to come to the graph here. And 1, 2, 3 at pi over 4. There's our first petal. Morgan, do you know how far apart our petals should be? Like how far apart they need to be. So how many petals do we have? Yeah, so our petals, we're gonna take 2 pi and divide it by 4, which is pi over 2. So each of our petals are going to be pi over 2 apart. All right, now we started here at the pole. So watch me draw this, please, and please count how many times I hit the pole. Ready? Thank you.
1, 2, 8,
What?
8,
What?
6.
Whoa! Let's do this again. Okay, I'm gonna start at the pole with 1. We hit it again, 2. Whoops. 2, 3, 4, 5. There are 5 zeros. Man, I thought they were gonna be the same number of petals as zeros. Well, when you start at the pole, you're gonna have an extra 0. Okay. All right, so we gotta find 5 zeros. Only for our sine roasters. So to find our zeros, we're gonna plug 0 in for R, and we need to find 5 of them. Okay. So I'm gonna divide the 3 over, sine of 2 theta equals 0. All right, so I need to figure out 2 theta equals. When is the sine equal to 0? And we need to start listing them off in order. The first place sine of 0 is 0, and then, and then, and then, and then. Okay, we now have 1, 2, 3, 4, 5 numbers. So now we can divide both sides by 2. Our zeros occur at 0 divided by 2, pi divided by 2, 2 pi divided by 2, 3 pi divided by 2, and 4 pi divided by 2. Okay, so look at right here, the sine equals 0. So the sine is 0 at 0, and pi and 2 pi. I list all the places where this function is equal to 0. Unit circle. So if we go around the unit circle, the y value is 0 at 0 and pi and 2 pi and 3 pi. We can just keep bouncing around and around and around. Okay, what questions do you have? Yes.
You go over the significant points again.
Yes. So in the case, well, we always are going to start by plugging 0 in for theta. Okay, so up here in this example, I plugged in 0 and we got 5. I plotted that point, and since it was the length of the pedal, I could just figure out where the other pedals are. In this example, since the sign of 0 is 0, when I plugged in 0, I got 0. Starting at the pole, I have no idea where my pedals are. So since we have a sine rose curve, I plugged my max R value in for R to solve for the angle in which I could make a pedal. Okay. So I had a third example. We have 4 minutes, and so I think we're just going to stop there, and I think that'll be okay. We have a worksheet.